All right, diving in today, and we're going deep on AI and medical imaging.
Sounds intriguing.
Yeah, it's cutting edge stuff, actually. There's this new AI method
Okay.
called ProjectedEx, and the aim is to basically improve how we diagnose prostate cancer.
Using MRI, right.
You got it, MRI images?
That's a huge area,
It's,
you know?
it is.
Prostate cancer affects so many people globally, so any improvement in, well, early and accurate diagnosis,
Mm,
it's really a win.
absolutely.
And what's exciting about ProjectedEx is that the goal is to make AI's insights, the things it's seeing in those images,
Yeah.
clear for the doctors, for the clinicians who actually need to use them.
Yeah, because you can imagine AI is so powerful for looking at these really complex scans,
It is.
picking up on things that maybe even a trained eye would miss.
Right.
But if you don't know why the AI is saying, hey, this looks suspicious,
Exactly.
then the power is kind of limited.
Absolutely. You need that interpretability.
Yeah, so that's what we're really getting into today.
Yeah.
The paper is called ProjectedEx, Enhancing Generation in Explainable AI for Prostate Cancer. So we're going to try and unpack this whole idea of explainable AI
I like it.
and see how ProjectedEx fits into that.
Because even the most accurate, like, AI classification, saying cancer, yes, cancer, no.
Yeah,
It's not enough for a doctor.
Right.
A doctor needs to see, why did it say that?
right.
What in this image led the AI to that conclusion?
Exactly.
So they can then validate it and make the best decisions for you, the patient.
Okay, so let's back up a little bit, set the stage.
Yeah.
We're talking about MRI to look at the prostate.
Yeah.
Some of us, myself included, are not experts in medical imaging.
Of course.
So can you give us a quick overview? Why is MRI so valuable here?
Yeah.
And what are these different types of scans actually showing us?
Absolutely. So MRI is fantastic for the prostate because it gives us really detailed pictures of soft tissue.
Okay.
And that's what we need to examine the prostate gland.
Mm-hmm.
So we use a few different MRI techniques. The first one is called T2 weighted imaging, T2WI.
Okay.
And this gives us a very clear anatomical picture.
Okay.
So doctors can look at that and say, okay, are there any unusual areas?
Yeah.
Has the cancer maybe spread beyond the prostate? It gives us a roadmap of the prostate.
So that's like our initial visual guide.
Exactly.
Okay.
Then we have what's called diffusion weighted imaging, or DWI.
Okay.
And we look at something called apparent diffusion coefficient, ADC, maps with that.
Okay. Now, what are those showing?
So those are looking at how water molecules move within the prostate tissue.
Okay.
And what we see is that in cancerous areas,
Yeah.
that movement is often restricted.
Okay.
So it shows up as a bright spot on DWI, dark spot on the ADC map.
Got it.
And that's a strong indicator of potential malignancy.
So areas where that water can't move around as much,
Right.
that's a red flag.
Exactly.
Now, you mentioned one other imaging technique.
Yes. So the third one is T1 weighted dynamic contrast enhanced imaging, or T1DCE.
T1DCE.
Yep. So Fatima, we inject a contrast agent into the bloodstream,
Mm-hmm.
and we watch how it flows through the prostate.
Okay.
Areas with tumors often have different blood flow patterns, so that can provide additional information.
Got it.
Now, there is a faster contrast-free version.
Oh, okay.
It's called biparametric MRI, or BP-MRI,
Okay.
and that just uses the T2WI and DWI-ADC.
So we've got all these different techniques,
Right.
but ultimately it comes down to a doctor looking at these images and saying,
Exactly.
okay, this is what I see.
This is what I think.
And that's where AI can step in.
It can, but as we said, it's critical to understand why the AI is saying what it's saying.
Yeah, that why is really important.
It is.
And that leads us to this idea of explainable AI, or XAI.
Explainable AI, it's a mouthful,
It is.
but it's about making those, really complex AI models more transparent. So we can see how they're making decisions.
Yeah.
And in medical imaging,
Yeah.
that's critical.
He's gotta
You
be.
need to be able to trust the AI's predictions. And that trust comes from knowing how it arrived at that prediction.
Exactly.
So clinicians can validate those insights and feel comfortable using that to guide the care they provide.
Okay, so the paper mentions an existing method called StyleX.
StyleX.
So what is StyleX, and why isn't it quite the right fit for something as complex as analyzing prostate MRIs?
So StyleX is a framework that's trying to explain how image classifiers make their decisions. It uses something called Steilgen's style space,
Okay.
and it tries to identify visual characteristics that the classifier thinks are important,
Yeah.
and then shows how changing those would change what the classifier says.
Okay, so if I'm picturing like a cat versus a dog image,
Yeah, exactly.
it could be good at doing that. So what's the challenge when we apply that to a prostate MRI where the signs of cancer might be much more subtle?
Yeah, so medical images, especially MRIs, they're just really complex. And the features that show disease can be very subtle.
Yeah.
So StyleX, which was kind of designed for these more natural images, sometimes struggles to make changes in these medical images that actually make sense clinically.
Okay.
And can explain the AI's reasoning.
So it's like the visual language of a medical scan is just different.
It's totally different, yeah.
And that's where ProjectedEx comes in.
That's where ProjectedEx comes in.
Right, so ProjectedEx, new approach designed to kind of tackle these limitations.
Exactly.
The paper highlights 3 main contributions of ProjectedEx.
Okay.
So let's go through them.
All right.
The first one is it's described as a generative framework that provides interpretable multi-attribute explanations.
Lots of big words.
So unpack that a little bit. What does that actually mean if I'm looking at an MRI and an AI's output?
Okay, so let's break it down.
Yeah.
Generative framework means it can actually create new images based on what it's learned from the MRI data.
Okay.
Interpretable means these images and the changes it makes are designed to be understandable by humans.
By doctors.
By doctors, by radiologists, by urologists.
Yeah.
And multi-attribute explanations means it can highlight several different things in the image that are influencing the AI's decision, not just one thing.
Got it.
So the goal is to link what we see in the MRI to why the AI is saying this is low risk or high risk for cancer.
So it's not just saying high risk,
Right.
But it's saying, hey, look at this area. Here's what I'm seeing.
Exactly. Maybe a change in tissue texture, maybe a change in how the water molecules are moving.
And that's why I'm saying high risk.
Yeah, it's making that connection between what the AI is seeing and what's actually important clinically.
Okay, I like it.
So the second key contribution is this enhanced encoder module using feature pyramids for multi-scale feedback.
All right, that sounds pretty technical.
It does.
So break that down for us. What's the core idea there?
Okay, imagine looking at a map, right? You can see the big picture, the cities, the roads.
Yeah.
But you can also zoom in and see individual streets, buildings, that kind of thing. That's what this feature pyramid idea is doing. It's letting the AI look at the MRI at multiple levels of detail.
So from big picture down to the fine detail.
Exactly. And the multi-scale feedback part means it's using the information it gets from all those different levels to refine its understanding.
So it's like getting confirmation.
It's like getting confirmation.
What I'm seeing at the big picture level
Right.
makes sense when I zoom in as well.
Exactly. And that helps it build a more robust understanding and generate better explanations.
So more trustworthy explanations, is that the idea?
That's the idea.
Okay.
And then the third key contribution is that they really put ProjectedEx to the test. They did experiments to demonstrate its relevance, its effectiveness.
Yeah, not just developing it, but seeing if it actually works.
Exactly. They looked at how well it could generate these visuals and how accurate the underlying AI was.
At classifying the images.
At classifying the images, exactly.
Okay, so let's get a bit more into the mechanics of how this all works. It uses this encoder-decoder structure with a feature pyramid, as we talked about, but also something called multiple discriminators operating at different resolutions.
That's right.
So what are all these pieces doing?
Okay, so the encoder you can think of as taking that complex MRI image and boiling it down to a simpler set of features.
Okay.
Kind of like a fingerprint.
Got it.
The decoder then takes that fingerprint and tries to reconstruct the original image or generate a new one, highlighting what the AI thinks is important.
And that feature pyramid encoder, it's extracting those fingerprints, as you called them, at different levels of detail.
Exactly.
Okay, now what about these discriminators?
So the discriminators are like the quality control.
All right.
There's one at each of those different levels of detail. And their job is to make sure that the images the decoder's making are realistic. And consistent across all those different levels.
So it's not enough to just look good at first glance. It's got to hold up even when you zoom in.
You got to be able to zoom in and still have it make sense.
Now, there's also this element called differentiable random projections via cross-channel mixing.
CCM.
Or CCM. Very technical.
It is.
But what's the idea there?
So think about the MRI image as having different channels. Different types of information. One channel might be the T2 signal, another might be the diffusion properties. CCM is a way for the AI to look at a mixed up version of those channels. This prevents it from getting too fixated on very specific combinations of features. and helps it focus on the more general patterns that really matter.
So instead of saying it involves applying a random one-by-one convolution to mix feature channels?
Right. Too technical.
We can say it's a way for the AI to look at like the texture, the intensity, in a slightly scrambled way.
Yeah, but still understandable.
But it's not getting hung up on like one tiny detail.
Exactly. It's seeing the forest for the trees.
Okay, I like that.
Okay, good.
Then we've got style space construction.
Style space.
How does this contribute to generating those explanations?
So the style space is like this big control panel with, in this case, 514 knobs.
Okay.
And each knob controls a different visual characteristic in the MRI.
Right.
And the AI learns which knobs to turn to make the image look more like a low-risk or high-risk case.
So it's learning how to organize that control panel.
It is.
So certain settings equal.
Higher likelihood of cancer or a lower likelihood of cancer.
So by tweaking those knobs,
You got it.
we can see what features are really driving the AI's decision.
Exactly. And by looking at which knobs cause the biggest changes in the AI's prediction, we can then visualize what those changes look like in the MRI.
So you can see what the AI is focusing on.
Exactly.
Now, the paper mentions this kind of complex loss function.
Yes, the loss function.
Adversarial loss, regularization, reconstruction loss, classification loss. What's the point of having all of these things working together?
So that loss function, it's basically the rule book that guides the AI's learning process.
Okay.
So the adversarial loss makes sure the generated images are realistic enough to fool those discriminators. The regularization prevents the AI from overfitting, so it can work on new cases it hasn't seen before.
Got it.
The reconstruction loss makes sure the AI can recreate the original image from its simplified representation.
So it's actually capturing the important stuff.
Exactly. And then the classification loss ensures that the generated images retain the key features for distinguishing between low risk and high risk.
So it's like a multi-pronged approach to make sure the AI is learning to do what it's supposed to do.
It is. It's a balancing act.
Okay, so how did they test this?
They use the PICAI dataset.
The PICAI dataset.
Yes, a publicly available collection of prostate MRI images specifically for this kind of research.
Okay, and how did they define the different risk levels?
So they used the ISUP grade group system, which is a standardized way to grade how aggressive prostate cancer is based on biopsies.
And how did they group those into the low risk, high risk?
Right, so ISU grade groups 1 and 2. Those usually mean a Gleason score of 6 or 3 plus 4, which equals 7.
Yeah.
They group those as low risk.
Okay.
And then anything above that, grade group greater than 2. Gleason score of 4 plus 3, so 7 or higher, they call that high risk.
Got it. So they tested a few different AI classifiers. I know you said EfficientNet-B was kind of the top performer.
It was, yeah, almost 84% accuracy, notably higher than the other classifiers they tested.
Now, to measure the quality of the generated images, they used something called the FID score.
The Fresh Inception Distance score.
What's a good score there?
So a lower FID score is better.
Okay.
It means the generated images are more realistic.
Okay.
Closer to the real images.
Got it.
And ProjectedEx did really well.
Okay.
It consistently had much lower FID scores than the previous method, ResstyleX, across all the classifiers.
So it's producing much more realistic-looking images?
Yes, and clinically relevant, too.
Okay.
For example, with MobileNet V2, ProjectedEx got an FID score of about 117. ResstyleX was up at 178.
Okay, so a big jump.
A big jump.
And with EfficientNet-B, ProjectedEx got a score of just over 108.
Yep, big improvement.
Now, the paper also shows some visual examples of tweaking the style space.
Yeah.
And how that changes the AI's prediction.
Right, so they showed real MRIs that were initially classified as either low risk or high risk. And then by adjusting those knobs in the style space, remember, those are the attributes the AI has learned.
Right.
They could shift the AI's prediction.
Okay.
So they could take a low-risk image and make the AI think it was high risk.
By changing a certain attribute.
Exactly. And you could see what visual changes in the MRI were happening when they did that.
So it shows what the AI is picking up on.
Exactly. And they could also do the opposite, take a high-risk image and make the AI think it was lower risk.
Interesting.
Yeah, so it's like they're visualizing the AI's thought process.
So if doctors can see those changes, that builds a lot more trust in the AI.
Absolutely. It helps them understand why the AI is making a certain diagnosis.
Which could lead to better decisions about biopsies, treatment, all of that.
Absolutely, because it's not just a black box anymore.
So wrapping this up, ProjectedEx, it's a promising new approach to make AI for prostate cancer diagnosis.
Yep.
More transparent.
More understandable.
It uses that feature pyramid encoder, the style space approach, to create explanations that link specific features to the AI's conclusion.
Exactly. And the results they got with the PIC-AI dataset were really impressive.
Yeah.
Show that ProjectedEx is much better at making those visual explanations.
And it works well with these strong classification models.
Like EfficientNetB.
So for you, the listener, why should you care about this?
Well, prostate cancer is a big deal.
It is.
And better diagnostic tools mean more accurate risk assessments.
Yeah.
And potentially fewer unnecessary biopsies.
No one wants an unnecessary biopsy.
Exactly. And by making AI more transparent, we build trust.
Right.
And that paves the way for these tools to be used more widely.
Which leads to better care, more personalized care.
Exactly. It's all about empowering clinicians to make the best decisions.
And knowing why an AI is making a prediction is crucial for that.
It is. It can't just be a black box, especially in medicine.
Absolutely. So it's really interesting to think that ProjectedEx can pinpoint these features that are influencing prostate cancer risk.
Yeah.
Well, what else could we apply this to?
Right. What other subtle signs of disease could we uncover with this kind of explainable AI?
Maybe things we haven't even thought of yet.
Exactly. Maybe earlier detection. More personalized treatments.
Yeah, it's a really exciting prospect to think about. So thanks for joining us on this deep dive.
My pleasure.
Into ProjectedEx and explainable AI.
It's been fun.
It has. We'll see you next time.
See you then.